Let's get right into it. According to the World Health Organization, over 400 million people in the world suffer from diabetes, a disease in which the human body cannot regulate its own blood sugar. In the advent of modern medicine, diabetic patients can be treated by injecting insulin, a hormone which helps to regulate their blood sugar. In United States hospitals today, 1/3 of all medication errors are related to the administration of insulin. 62% of these errors are from improper nurse preparation. That is, the nurse does not prepare the correct dosage, type, or timing of insulin injections. Consequences of botched insulin injections can be severe, and 57% of all hospital dosage fatalities are from insulin errors. Nurses face several challenges which can cause them to improperly prepare insulin injections. For one, messy handwriting and inconsistent abbreviations in doctors' handwritten notes can cause misinterpretation of the required insulin dose. Poor log keeping can lead to duplicated doses or omitted doses. Confusing brand names also contribute to their difficulties. These factors are all exacerbated by the stressful and repetitive hospital environment. As a team of mechanical engineers, our goal was to combat the problem of insulin preparation errors by designing a machine that quickly, accurately, and automatically draws the correct dosage and type of insulin. Automation of the process could eliminate the critical human errors which plague conventional insulin syringe preparation. Benefits of an automatic syringe preparation system would be manifold. Not only would lives be saved, but extended hospital stays from insulin dosage errors would be reduced, saving time and money for the hospital and patient. The scope of the machine would encompass the entire syringe drawing process, ending with a fully prepared syringe ready for administration by the nurse. The machine would be connected to the internet, making use of the electronic health record in the cloud. Whenever a patient's barcode would be scanned on the machine, their prescription would be accessed and a syringe would be automatically prepared with the appropriate insulin type and dose. To assess how this automated machine would compare to existing practices, we took a look at how nurses conventionally prepare insulin syringes. For this, we made extensive use of tutorial videos and consulted professionals in the nursing field. The nurse must first obtain and read the patient's prescription. Throughout the process, the nurse typically double and triple checks the prescription. The nurse then selects the appropriate vial from storage and mixes the contents by rolling it between their hands. The nurse uncaps the syringe and sterilizes the top of the vial using an alcohol swab. The nurse then inserts the needle into the vial and draws the insulin, placing the vial back in the storage after the draw is completed. To compare the efficiencies of a nurse to that of our conceptual machine, we made conservative worst-case guesses for how long we expected the process to take for a machine using computers and motors, and also for a nurse. From the table at right, it is clear that a machine accessing data in fractions of a second and using specialized motors will outperform a human in most analytical and mechanical tasks. For example, a nurse would have to read the prescription several times over to confirm, taking nearly a minute, while accessing data from the cloud would take a machine less than a second. Furthermore, nurses make errors from time to time, which is while a properly programmed machine would seldom, if ever, make mistakes. Seeing the rough performance gains of a machine along with the accuracy which motors provide gave us confidence to move forward with our idea of automating the syringe preparation process and made us feel that this was a worthwhile problem to tackle. To assess the requirements for our machine, we again turned to professionals in the practice, investigating what qualities were most important. Naturally, safety was the #1 priority in a hospital setting, but the machine must also be easy to use and reliable. Qualities which related to the mechanical design of the machine are shown boxed in red here. We kicked off our design cycle on the back of this preliminary analysis, focusing on offering an end-to-end solution which maintains sterility, is highly accurate, and has a limited need for maintenance. Moving forward, I will present the final design which we arrived at after a 10-week design cycle, after which our team will present their individual contributions to the project. So I'm proud to present to you the Syringe Preparation System, or SPS, our solution to the error-prone insulin drawing process. It is roughly the size of a microwave and weighs about 40 pounds. While it is able to prepare an insulin syringe in an average of 38 seconds, it also acts as a storage device, holding up to 20 syringes and 60 insulin vials at a time. The design of the syringe preparation system was split into 5 subsystems. The first subsystem is the carousel, located at the top. It stores the insulin vials in a circular track. When a draw is requested, the carousel rotates to position the appropriate insulin vial above the syringe, such that the insulin can be drawn from it. The second subsystem is the spool, which holds the syringes. It rotates to align the syringes with the syringe manipulator. The syringe manipulator is responsible for manipulating the syringe, as the name might suggest. It moves the syringe up, puncturing the vial, and draws insulin into the syringe by pulling the plunger of the syringe. The enclosure protects the machinery from users and helps to maintain sterility. Finally, the electronics and wiring power the machine, connecting the subsystems to each other and to the internet, making this device a smart one. The machine has 6 degrees of freedom and 6 motors, which it uses to manipulate the syringe and draw an accurate dose of insulin. As previously stated, degrees of freedom 1 and 2 control the rotation of the spool and carousel. These are rotational degrees of freedom. These are used to align the syringe and the correct vial such that the syringe can be pushed upwards and inserted into the vial using degrees of freedom 3 and 4, which control the position of the vial. The degree of freedom 5 is used to uncap the needle, and degree of freedom 6 is used to dispose the used empty vials. Degrees of freedom 5 and 6 will be discussed in greater depth in following presentations. This video demonstrates the process by which the syringe preparation system draws insulin into a syringe. First, you will see the syringe cap removed. The carousel then rotates to align the appropriate insulin vial with the syringe. The syringe is then pushed up into the vial, and with a needle inserted, insulin is drawn into the syringe. See for yourself. There's uncapping, inserted into the vial, and now insulin is drawn into the syringe. I'll play that one more time. You can see at the end of the drawing process, the spool which holds the syringe rotates additionally. This presents the completed, fully filled syringe to the front of the spool, therefore allowing the nurse to open the device, reach in, and take and remove the prepared syringe from the machine. So I'm proud to, now that I've given an overview of the machine, I'm proud to introduce the team that worked on the design and analysis of this machine. Our team consists of me, Simon Rufer, Aidan Montiel, Ryan Miller, Emily Yang, Reana Naik, Cesar Ferrufino, and Cameron Gelber. Each member worked both on an aspect of the mechanical design and the analysis. You will now hear from each team member on their contributions to the project. From the motors. So let's dive right into the design of the syringe manipulator. As I said before, its primary function is to pull the plunger of the syringe downwards, such that insulin is drawn into the syringe. The design of the syringe manipulator can be seen at right. The mechanism is driven by a stepper motor, shown at the bottom of the figure, which attaches to a ball screw, which drives linear motion of the grasper, which is shown halfway up the ball screw. The grasper holds the syringe plunger in its tip, in the little jaws that you see there. When the grasper moves down, it pulls the syringe plunger down with it, drawing insulin into the syringe. Here you can see the animated motion of the grasper. As you can see, it pulls on the plunger of the syringe, drawing insulin into the syringe. So let's go a little bit more in depth about the specifications which drove the design of the syringe manipulator. The force required to draw insulin into the syringe was experimentally found to be 1.2 pounds. The maximum draw speed was experimentally found to be 0.45 inches per second, which is the speed at which bubbles were introduced in the syringe due to cavitation. The design of the syringe manipulator therefore had to produce greater than 1.2 pounds of force and be capable of linear motion at least 0.45 inches per second, such that the process could be done as quickly as possible without introducing bubbles. The syringe manipulator must also be accurate and repeatable, as drawing the correct dosage is the goal of this machine. A ball screw mechanism was chosen for this linear actuation because of the low backlash, superior life from its low wear surfaces, and smaller footprint compared to other actuation systems we considered, such as the rack and pinion and cam systems. A 3/8 inch diameter, 8 thread per inch ball screw was chosen as it was the smallest size found at a reasonable price. Combined with a NEMA 8-stepper motor, the ball screw actuator is capable of 9 pounds of axial force and a maximum speed of 4.2 inches per second, satisfying the design requirements. The resolution of the stepper motor enables an axial precision of less than 1/1000th of an inch, giving this mechanism a high degree of precision. We chose to exceed the minimum required force specification by a large margin, such that the possibility of the motor skipping steps would be greatly reduced. Nonetheless, an absolute encoder is included in the design to keep track of absolute position, such that skip steps can be accounted for, increasing the overall accuracy of the mechanism. Furthermore, recognition of skip steps with an absolute encoder could also trigger an e-stop in the software for abnormal conditions. Good engineering practices are upheld in the design by doubly supporting the ball screw with retained bearing stacks on either end. These bearing stacks transfer the axial load through the bearing housings as opposed to the motor shaft, increasing the overall repeatability and lifespan of the motor. The design of the grasper is shown at upper right. It has been designed with entrant features such that any play in the syringe plunger can be absorbed and accuracy can still be maintained. The figure shows the position of the syringe as a red dotted line as it passes through the grasper. As you can see, the entry of the grasper is wide before it tapers down. This allows plungers that are initially slightly displaced from their ideal position to be located at a centered position before actuation occurs just before the syringe exits the grasper. In summary, the syringe manipulator design holds much greater precision and speed than a human. It is capable of drawing insulin at the maximum possible speed without introducing bubbles into the syringe, but with an axial resolution of less than 1/1000th of an inch, which is not capable by the human eye. Let's move on to the thermal analysis of the motors. The first objective was to determine whether or not active cooling would be necessary at all for our machine. If it was deemed necessary, we sought to quantify the cooling needs and then design an enclosure and fan to meet these cooling needs. This analysis was driven by two key numbers. First, stepper motors convert a large percentage of the electrical energy fed to them into heat energy. Second, all surfaces of the product must remain below 40 degrees Celsius, because this is the minimum temperature at which skin burns can occur. The first step in the process was a functional analysis of the duty cycles of the motors. Here you can see a timeline of each of the 6 motors actuating in an average draw sequence. Green indicates that the motor is actively moving, and yellow indicates that the motor is holding position. The heating power of each motor was identified in the right column by combining the duty cycle from this analysis, motor efficiency, and motor power. 4 of the motors were identified as non-issues, as the heat they generated would be sufficiently dissipated by natural convection and radiation. However, the manipulator and body driver motors, which are highlighted in yellow in the timeline, had significant heat generations. They are both attached to the same plate underneath the syringe manipulator and spool. The heat generated by these 2 motors was further investigated, as it could not be dissipated by natural convection alone. So a transient thermal simulation was created to see if and when any components would exceed 40 degrees Celsius without active cooling. That is, using only natural convection to dissipate the heat of the motors. The defeatured model shown at right in the mesh included only the plate holding the motors and the spool and manipulator mount. Natural convection coefficients tabulated at left for each of the surfaces were derived from Rayleigh number correlations. Internal heat generation was applied to the motors, as you can see in the figure in the right, and the heat was dissipated through natural convection and radiation on the surfaces of the plate, spool mount, and motor mount. The results of the study showed that the plate indeed exceeded the 40 degrees Celsius limit after about 33 minutes of continuous operation. It was therefore determined that an active cooling system would be required. In order to quantify how much active cooling was necessary, a steady-state thermal model was built similar to the previous model, but including forced convection on the sides of the motor and the underside of the plate. The forced convection heat transfer coefficients were determined from laminar flow equations. The study was run multiple times, with the heat transfer coefficients varying as a function of far-field airflow velocity. It was found that at an airflow velocity of 0.2 meters per second, the maximum steady-state temperature was held below 40 degrees Celsius. The general scheme for the cooling was to enclose the two motors in a single rectangular enclosure, which was 2 inches by 2 inches in cross-section, which is shown by the red sketch box. Air would be blown through the enclosure and over the motors, as shown by the blue arrow indicating airflow, and this would be done with a fan. So a CFD model was created with the simple enclosure. As you can see at the bottom right, it's meshed, and the two motors are acting as flow impedances. The pressure drop over the 2 inch by 2 inch rectangular enclosure was found at the flow speed required for cooling of 0.2 meters per second, and it was found to be just half a Pascal. So a fan was specified which could reach a flow rate of 0.2 meters per second at a pressure drop of 0.5 pascals. So with this fan specified, and with the previous transient and steady-state thermal analyses, we are confident that we have reached a sufficient cooling rate such that none of the components of our machine exceed 40 degrees Celsius and cause any harm to any users.
Hello. The first major component I worked on after helping Simon with the manipulator design was the syringe body driver. On the left, there is the full syringe driver assembly, and on the right, a section view of it. The syringe body driver functions to move the body of the syringe in conjunction with the manipulator. The combined actuation of these two motors allows the syringe to be moved up and down without moving the plunger in relation to the rest of the syringe. In this design, rotational motion from the stepper motor is converted to linear motion using a ball screw and nut. Flange is threaded onto the ball nut that is used to intercept a peg on the syringe rail system. Once the peg is rotated into place in the ball nut flange, it is able to be moved by the actuator. Attached to the flange are two threaded track rollers. These rest against the spool body and restrict the flange from rotating. The track rollers have lubricant sealed inside of them and are maintenance-free. The stepper motor is mounted to the base plate with screws. To reduce axial load on the shaft of the stepper motor, a ball bearing is used, seen on the right. The bearing is press-fit into the base plate and secured on bottom with a lip and on top with a C-clip. Any force pressed down on the ball screw will be transferred to the base plate through the ball bearing. Any force exerted in the upward direction on the ball screw will be transferred to the base plate through the C-clip. A custom shaft coupler is used for the motor and ball screw. The ball screw is secured with two set screws. The motor shaft is a D shaft and slides into a D-shaped hole in the coupler. This allows the coupler to slide up and down small amounts to ensure all load is transferred to the base plate and none is transferred to the motor shaft. The second thing I worked on were the electronics and wiring for our system. Electrical components for the syringe preparation system include 6 motors, a cooling fan, 1 absolute encoder, 1 UV light, 6 motor couplers, 120-volt AC to 12-volt DC power supply, 1 Arduino Mega, and a 12-volt to 5-volt voltage regulator. Stepper motors of various sizes are used for all actuation due to their precision, power, and ease of use. One drawback to stepper motors is the heat that they generate. The Pololu A4988 motor controller allows power restriction to the motors when they're not in use, allowing them to cool. An absolute encoder will be used on the syringe drawing motor to ensure the accuracy of dosages being drawn. A 12-volt UV light ring is used to sterilize the caps of each vial, ensuring the safety of the patient. Thermal simulations suggested that heat from our two motors would create a potentially hazardous surface temperature on the base plate during a heavy-duty cycle, so a fan has been included to solve this problem. An Arduino Mega is used as the microcontroller due to its abundance of digital and PWM ports. A reed switch is used as a sensor for the main door of the device. This ensures all systems refrain from movement while the door is open to maintain safety and sterility. This is the wiring diagram for the full syringe preparation system. The Arduino Mega controls 6 motor controllers, one for each stepper. Those controllers allow the steppers to be actuated in the forward or reverse direction, as well as hold a position and turn off. The motors are powered by a 12-volt DC signal from the power supply. The controllers and single encoder are powered by the 5-volt signal. The reed switch is used in conjunction with a resistor so that when the switch is closed, the Arduino will read 0 volts, and when it is open, it will read 5 volts. The UV LED is also powered by a 12-volt DC supply, and both DC power sources are grounded to the frame of the device. This is a flat diagram of our wiring system. The syringe manipulator, syringe driver, spool, uncapping motor, carousel, and vial disposal identify different stepper motors. Wire bundles connecting stepper motors to the electronics box are 4-wire high flexibility bundles, shielded, and 18 gauge. UV light, power supply, and fan are connected to the electronics box with 12 gauge wire, 2-wire bundle shielded cables. All connections within the electronics box are done with jumper cables and are not shown on the diagram. Power supply and Arduino are connected to the external ports via their factory connection cables. Wires are secured to the clips as shown. Clips are secured to the frame of the device using an adhesive reinforced with epoxy. This image shows all the paths and orientations of the wires in the system. Wires for components in the bottom half of the system run along the base plate to its pivot point, then along the left, back, and right inner walls of the system until they enter the electronics enclosure. Components in the top half of the system are wired along the bottom of the carousel support plate, along the right wall, then onto the electronics enclosure. The power and USB ports are located on the right wall in front of the electronics enclosure. The third thing I worked on are system renderings. These 3 show the full assembly of our system with the door open and closed and the inner light on and off. These 2 show the assembly stripped of the enclosure. The left has coverings for the manipulator and the base plate, and in the right they are removed so you can see the systems that lie underneath them. These are close-ups of 3 of our systems: the spool, the carousel, and the manipulator.
Hello, my name is Ryan and I'm a current 4th-year mechanical engineering major at UCLA. I was in charge of the spool design and Simscape analysis. The role of the spool in our design is to house the unused syringes and, when the time comes, manipulate the position of the unused syringe to align with that of the vial to draw the correct insulin type and amount into the syringe. Early design ideas for the spool were bulky and full of excess material. One of the early spool design requirements that we defined was its ability to be easily replaced. When the total allotment of syringes has been utilized, it must be easy for the nurse or technician to replace the entire spool, thus replacing the machine with new syringes. We wanted to make this process as easy as possible for the nurse, so we designed a spool that could be easily removed and replaced in its entirety, instead of the nurse having to replace each specific syringe. Thus, the spool is only supported at its center, connecting down to the motor housing shaft. A simple hex nut is placed at the top to ensure no vertical movement that may be caused by vibrations while operating. To replace, the nurse simply unscrews the hex nut, removes the entire spool, and replaces it with a new one. To ensure alignment, an off-center cylindrical shaft is placed on the connector piece, acting as a medium between the motor housing and replaced spool. Due to the need to have a spool fixed only on the motor shaft to allow for easy replacement, I needed to work to alleviate the axial loading on the motor shaft. To do this, I introduced a shaft coupler and ball bearing. The ball bearing uses a retaining ring to form a housing inside the motor shaft. This allows the axial loading force to be redirected onto the motor housing instead of its own shaft. The inner portion of the ball bearing, spinning due to the rotation of the motor shaft, transfers the rotational energy using a connector piece and then shaft coupler. On the other side of the shaft coupler, another connector piece is fastened to allow the replacement of the spool to be placed and aligned on the connector, and the axial loading displaced to the motor housing. To ensure that the motors were correctly spec'd and worked as intended, we decided to run a Simscape multi-body analysis, simulating the loading conditions applied to the stepper motors. In total, we built models for 4 of the motors: the Carousel, Spool, Mani, and Syringe Body Driver. Building a stepper motor model allowed us to export all of the joints and constraints from SolidWorks into Simscape and concatenate the stepper motor model with the mechanical models. To ensure smooth profiles for the stepper motors, I went ahead and used Dr. Rosen's graduate robotics class to define velocity and position profiles for each of the steppers. These trajectories were used to ensure smooth profiles in an attempt to decrease the overshoot when the motors are operating and to try and speed up the overall timing of the syringe filling iteration. A quintic polynomial technique was used to define the velocity, position, and acceleration profiles. Once these curve functions were defined, we needed to work to create the actual pulse trains that replicated these trajectories. In the stepper motor model, the controller takes in a constant, representing the total number of steps to be fed to the stepper. The controller takes this constant and creates a fixed frequency pulse train. To create our own pulse train with varying frequency, we decided to tweak the controller and introduce a stair generator. The stair generator allowed us to manipulate and create our own pulse trains that varied in frequency. We defined amplitude and time arrays that were stored in the stair generator to create our own pulse trains. Using the previously designed position profiles, we created a step every time the position profile reached another factor of 1.8 degrees. Using this optimization, we were able to obtain very good results in our motors, decreasing the overshoot and decreasing the settling time for the motor dynamic response. Here is a complete model of the carousel. The bottom right portion of the model represents all of the multi-body portions that we extracted from the simplified SolidWorks models for the carousel. We use our own defined pulse trains inside the stepper controller to actuate the revolute joint created between the two moving components. To make this model simpler, we created 2 parts from the entire carousel model, representing the components on either side of the motor shaft. Thus, the revolute joint represents the joint between the motor shaft and the entire carousel assembly. This joint is actuated by the pulse train, and we can view the subsequent position, velocity, and torque profiles of this joint under the carousel loading conditions. Although only one model was created for the carousel, 2 different simulations were run, representing the minima and maxima positions that the carousel would have to rotate. Here we analyze the results of the small displacement simulation for the carousel model. The position graph shows that the final position of the carousel is indeed the correct 36 degrees. Since the syringe is not yet placed inside the vial, the small amount of overshoot the system experiences is not of concern. To ensure correct alignment between the syringe and the vial, we spec the small movement of the carousel to take about 1.6 seconds, so that it is settled before attempting to insert the syringe. The velocity profile somewhat represents that of a trapezoid, with small disturbances being introduced due to the nature of the stepper motor and dynamics of the carousel model. Likewise, the torque graph makes sudden jumps due to the nature of the steps being introduced to the motor, and the motor is spec'd to be able to withstand the torque limits graphically shown in the torque profile. We thus conclude that the motor is spec'd properly to be able to move this load at an angular displacement of 36 degrees. The second set of results presented is for the extreme condition of the carousel motor, where the carousel has to rotate 180 degrees to access a vial on the opposite side. In this model, the actual step rate and pulse profile was found iteratively to ensure the motor did not skip any steps. Thus, to ensure no steps were skipped, we had to provide a subtle ramp up in the motor to its final position of 180 degrees. As a result, it takes almost 6.5 seconds to finish the entire movement of the carousel when reaching vials on its opposite side. The velocity profile here represents a moving trapezoidal profile with small oscillations protruding due to the nature of the stepper motor and taking discrete steps. Thus, the torque graph also resembles this quick oscillatory behavior. The motor is spec'd to meet these torque limits, and thus the carousel motor is spec'd properly to carry out both of its extreme conditions. In conclusion, using Simscape allowed us to verify that all of our motors are able to operate as prescribed and can handle loads of the model to perform their desired tasks. With this analysis, we were able to find the total time it takes for the system to carry out its task. Although we were able to calculate the time it takes for the displacements to occur, we needed to analyze the overshoot parameters being introduced into our model to allow our system enough time to settle before the next function could be initiated.
Hi, I'm Aidan, and I'll be giving a brief overview of my contribution to the project. I worked on the spool design, and the purpose of the spool is to house the syringes and move them to and from the manipulator for drawing. This was a new feature once we were no longer manufacturing the product and could pursue a more complex system. And originally we were trying to figure out a passive way to do this. One idea we had was to have a spring-loaded storage system that would push new syringes forward once a syringe had been grabbed, similar to the operation of a vending machine, but it ended up to be a simpler and more precise solution to just make an active system. And we decided that the most efficient and compact method to store the syringes was around the edge of a ring, and we ended up calling the system the spool. And the final product is shown here. So I modeled the frame of the spool and the sliders for each syringe. So starting with this frame, the design is pretty simple, just a top and bottom plate attached by 4 rods screwed together with steel shafts for the sliders to move along. And there are 2 rows of shafts so that the sliders don't rotate while moving. The spool can fit up to 20 syringes. We wanted to make sure there were enough syringes so healthcare administrators don't have to constantly refill the syringes, but the system still had to be compact, so this spool size was a good compromise. Also, the diameter had to be large enough to accommodate the size of the syringe driver that moves the syringes along the shafts up into the insulin vial. Moving on to the slider design, the slider has 4 main components. Starting from the left, the first component is the syringe plate, and obviously that's where the syringe clips in, and the syringe flange fits into the bottom slot to prevent any vertical motion once the syringe is clipped. And the plate is then fastened to the main body, which also acts as the housing for 2 linear ball bearings, which slide along the steel shafts mentioned earlier. Finally, there's a small grab tab at the back, and that's where the syringe driver grabs in order to move the syringe up and down along the steel shafts. The modular design was made with ease of manufacturing in mind, and it also makes parts easy and cheap to replace if they fail. The main body and the grab tab can be machined out of aluminum, and the syringe plate would be made out of a plastic such as nylon. And the plates will be in contact with the healthcare workers and any outside contaminants the most. So that's why we want to make sure that they're the cheapest and easiest to replace for sterility purposes. So the analysis I worked on was Simscape, which is a software offered by MATLAB. We use Simscape because it allows you to import SolidWorks models with Simscape Multibody and perform a more detailed dynamic analysis than you could achieve solely with SolidWorks. And the first Simscape model I made was for the spool, which you can see here. The goal was to make sure our motors were strong enough to move the system at the speed we needed. So on the left side of the model, you see a stepper motor model, and that's where you can input specifications of your stepper motor, And then on the right are the multi-body blocks, which are generated from your imported SolidWorks model. So here I was focusing on the revolute joint because that's how the stepper motor would be spinning the spool. Looking at the results, as you can see, there's a small amount of overshoot in the position plot due to the dynamics of the system. I also have the velocity and the torque plot shown here. And we worked to see if this overshoot could be eliminated by varying the step rate while the motor was in motion, kind of to achieve an ideal trapezoidal shape with a velocity curve, but it proved to not have a huge effect on the performance. Ultimately, there was no way to completely eliminate the overshoot, but given the overshoot, the spool settles to an equilibrium position within about a half a second. So the total motion from start to end is only around 1 second, which was an acceptable time. The second model I made was for the manipulator, and here my focus was on two main areas. The first is the revolute joint highlighted, and right under that is the lead screw, which connects the plunger block to the ball screw. And you'll see that design in the next slide. So these are key to making the model function like the real-life system. And looking at our results, I was focusing on the vertical motion of the syringe plunger block from the motor and ball screw, which you can see on the left. Additionally, I applied an outside spring damper force to the block to model the resistance from the syringe plunger during drawing. The goal here was to check the speed at which the plunger block could travel when being driven by the stepper motor with a ball screw. The max speed that we could reach without the motor slipping was 6.7 millimeters per second about, and the specification we calculated for the necessary drawing speed was 4.5 millimeters per second, so that requirement was well met. The motor was also able to achieve this smooth motion with negligible or no overshoot and oscillation, which you can see from our position plots. And yeah, that was my contribution to the project. Thank you.
The motor attachment design is an elegant approach for reconciling the NEMA 17 stepper motor with both the carousel and the enclosure. The motor shell itself serves to shield rotating parts and at the same time attaches the carousel subsystem to the rest of the enclosure. The motor shell also features a shaft for a ball bearing, and the reason why we incorporated a ball bearing was to avoid transferring the axial load from the carousel to the motor directly. The attachment to the carousel functions as a torque transfer mechanism between the motor shaft and the carousel, which allows it to rotate smoothly. The previous iteration of the design involved the motor being attached to above the carousel plate, as shown in the figure on the right. It was a space-effective solution. However, since the carousel will always rotate, it would cause issues for wiring. Therefore, I switched the position of the motor so that it was under the carousel plate instead, which is less so a space-effective solution, but it makes wiring a lot easier. For motion analysis, we decided to produce mechanical visualizations of 4 different mechanisms: the single draw, double draw, vial disposal, and spool replacement. The timelines for the single draw and double draw are shown below. I used motion analysis to create the most efficient timeline of events that are physically achievable by the system. The single draw and double draw are the highlights of the syringe preparation system and are relatively complicated since every single component, minus removing the prepared syringe from the spool by the nurse, is automated and has to follow a specific order of actions. If one step is out of order, the syringe could draw incorrectly. These are similar timelines for the vial disposal and spool replacement. The spool replacement is different because it is entirely a manual process, while the vial disposal is completely automated, similar to the single and double draw mechanisms. I calculated the required step rates for the syringe manipulator plunger driver and spool syringe body driver based on the 6.7 millimeters per second we had specified that was required to accurately draw insulin. The reason the step rates are the same for both drivers is because when the syringe is being uncapped or being inserted or removed from the vials, the drivers must move simultaneously. The only time the drivers do not move simultaneously is when the plunge driver moves down to draw insulin into the syringe. The 422 steps per second was then confirmed with Simscape analysis. The step rates for the carousel, vial disposal, and syringe uncapping were arbitrarily chosen to match standard values for step rates, since both mechanisms don't involve load-bearing components. The spool rotation and carousel vial rotation step rates were directly determined from Simscape analysis. Based on these step rates, I calculated the maximum time it would take to perform each action in the 4 mechanisms mentioned before. The maximum time to prepare a syringe, which would normally correspond to a double drawing mechanism, is 43.70 seconds. And the minimum time to prepare a syringe, which would normally correspond to a single drawing mechanism, is 33.49 seconds. One interesting thing to note is that the step rate differs depending on if the carousel is rotating to the adjacent vial versus if it's turning a full 180 degrees to the opposite side. For the adjacent case, the step rate is 18.7 steps per second, determined from the Simscape analysis. However, the same analysis also shows that to move 180 degrees, the average step rate needs to be 17 steps per second, without making sure that the stepper motor does not skip a step. The increase in time due to the reduced step rate would approximately add half a minute to both the values I had mentioned below. This is a representation of how a single drawing mechanism would work. And similarly, this is how a double drawing mechanism would ideally work. One very important limitation of our system that I discovered during motion analysis was the fact that the system is unable to draw insulin to the syringe full capacity. We specified that our system should be able to draw up to 2.36 inches of the syringe, which corresponds to the 100 units of the syringe. However, the system and the way it is designed will only allow an axial displacement of 1.5 inches of the syringe. This is because once the plunger holder moves down while drawing, it can only move a certain additional distance downwards when the syringe is fully drawn, shown by the blue line in the figure. However, that distance does not fully allow the syringe needle to clear the hole in the enclosure through which the needle is inserted into the vial, which means the syringe is essentially stuck in the machine. Therefore, the limit is 1.5 inches, which corresponds to 60 units maximum draw. Based on the recommendations from the National Center for Biotechnology Information, the NCIB, the average dose of a human that they would need per dose is 18 units, which is well within our capacity. And that is a short summary of my main contributions to the project.
Hello, my name is Cesar Ferrufino, and I primarily worked on the design of the carousel. We had to address vial disposal and refilling in addition to vial placement as part of the expanded requirements from the move to virtual. In the initial design phase, the vial disposal was towards the center of the disc. That is, vials would be pushed towards the center into a hole with a solenoid and fall into another area for disposal. Unfortunately, I did not keep the CAD models of the earlier designs, so we will have to settle for hand drawings. In the early designs, the carousel would rotate to a fixed position where a solenoid was. Then it would push the bottommost vial towards the center for disposal. The solenoid would be in the way of the top vials until it retracted, where the vials could fall into place by gravity. This idea was scrapped because there was concerns about finding a solenoid strong enough, small enough, and with enough reach to meet the refilling requirement. In the next design, the excess vials were held in a separate structure from the cylindrical holder. Solenoids would be at the top of each refill tube to be activated. This was not kept because it required a lot of solenoids and did not significantly improve on the earlier iterations' drawbacks. The next design still had vial disposal towards the center, but another mechanism that would have held the solenoid and rotated. This was complicated and didn't improve much. The next major design phase was moving the vial disposal and refill along the tubes that house the vials, rather than a hole in the middle. In this phase, the carousel resembled the design we have now with a few key differences. We had two of the retaining mechanisms for the vials, the clips holding the vials open inward, and the jaws were forced open with a solenoid at a fixed position. Some of the elements of this design were retained in further iterations, but it was primarily scrapped because of the accuracy requirement for the stepper motor. We could not get the vials close enough using this design. That is, the minimum diameter at which the vials were located was too large with this design. Additionally, this was complicated as it would require two sets of spring-loaded mechanisms. The designs shown here are the same, except they had different clip designs. That brings us to the current design. Refilling would no longer be done with a solenoid, but with a pseudo-subsystem, the refill plunger. The vials would be pushed from the top to force the spring-loaded jaws to open. The jaws could now open towards the outside of the cylindrical structure, which allowed for the vials to be packed in much closer. After the jaws were forced open, the vials would fall down until the bottom one cleared, at which the jaws could snap back into place fast enough to catch the falling stack. The clips are designed in such a way as to allow the cap to fit through. Overall, the design of this system took longer because of the optimization of space that needed to bring the minimum diameter down. That brings us to the refill plunger. At its heart, all the refill plunger needs to do is push down on vials and return back to its initial position. In the very early stages, we thought of using some linear actuator right above the point of disposal, but that took up a lot of space. Then we took a similar approach as to the manipulator and picked out a long ball screw. A ball screw rotates a ball nut that is held rotationally fixed by another axle. The ball nut cannot rotate, so when the ball screw rotates, it is forced up or down instead. Initially, the ball screw was mounted directly onto the stepper motor and towards the top. However, due to loading concerns of the stepper motor housing, the ball screw was instead mounted onto a bearing assembly that was coupled onto the stepper motor shaft. To make wiring easier, and because of the extra space the motor had towards the bottom, it was swapped towards the bottom of the assembly. There wasn't enough clearance as needed, and the motor mount at the bottom ended up interfering with the spool. At this point, a frame was also added to provide additional support and a surface to clamp onto for alignment. The motor still had to be mounted at the bottom, but now it was moved off the ball screw axis, necessitating the use of gears. This was still not good enough because given where it was located, the whole design needed to take up less space. It was too close towards the edges of the base plate, which were needed for the framing of the enclosure. I had to swap out the ball nut used, reduce the size of the mounting plates, and swap out the ball nut holder. From the motion analysis, the ball screw selected was too slow for refilling. For its worst case, the refilling took minutes. Another last-minute design change was replacing the ball screw with one that had more travel per turn. This meant replacing the ball nut holder, and the bottom mounting plate. These things ended up interfering with each other and needed to be changed to accommodate this ball screw change. Now refilling for the worst case scenario is much faster, about 2 seconds. I also worked on making the drawings for the carousel and the refill plunger, and also fixing CAD errors during when completing the integration.
Hello, my name is Emily, and I will be presenting on the system enclosure as well as motion analysis done for the vial and spool replacement mechanisms. So the enclosure was designed with a few considerations in mind, such as sterility, subsystem placement, accessibility, and modularity. The enclosure is divided into two compartments. The upper enclosure is to house the carousel, and the lower enclosure is to house the spool, manipulator, and electronics. The compact design aims to be both cost-efficient and space-efficient, especially for use in small used in smaller medical facilities. The upper enclosure features an ABS plastic housing that stands 16.2 inches tall, and it shelters both the carousel system and the refill plunger. The pull-off lid of the carousel housing is lined with a rubber seal to maintain easy access for vial replacement as well as tight concealment to ensure sterility. The lower compartment resembles the size of a small conventional microwave and features a range door with a viewing window. The outer casing of the lower compartment is also manufactured from lightweight ABS plastic. The lower enclosure top is designed to be fastened separately via a series of tab-in slots as well as four-corner flathead screws. This allows access to the top enclosure base plate. Although the top enclosure base plate is not directly shown on this slide, it is a very important piece. It serves to connect and align the carousel with the spool and the manipulator. It also is a sturdy fixture for the refill plunger and the uncapping motor and the UV light. So our choice of maintaining a sterile environment is to use the UV light, and this is for several reasons. One of them is that the method of sterilization requires only 10 seconds to fully sterilize a component in a compact environment. And in this case, vials are very small. Each vial is very small, so UV light is perfect. And the UV light will not cause damage to the vial tops, the syringe needle, or any of the aluminum framing. In fact, any metal objects are safe from the UV light. To maintain common sterility practices in the hospital, the sterile environment is placed on top of the non-sterile environment. So here we have the structural support of the lower compartments. So the structural component has a dual function of acting as both support for the carousel and as a mounting rack for the spool base plate, the range door, various electronic systems, as well as fasteners for subsystem placement. The structural frame is constructed by solid aluminum 1x1 inch T-slot bars of various lengths. Each aluminum bar has a yield strength of around 35 kpsi, which far exceeds the 20-pound load requirement calculated for the carousel and the refill plunger. The T-slot bars are arranged to form the frame of a cube using three-way T-slot fasteners, as well as L brackets to secure in place. T-slot screws are then used to attach variable mounting rails. With modularity in mind, these rails are adjustable in height so that the power supply unit, the PCB enclosure, and the cooling fan can be easily mounted to fit the user's needs. Future design improvements such as an interactive user interface and an automated barcode scanner will require additional electronic systems. Therefore, the mounting rails are ready to be adjusted accordingly to accommodate these additional changes. The mounting rails also take into account of the tight enclosure spacing and are designed to keep wiring away from the user to avoid any unwanted tampering. Electronics can be accessed by the user via the side panel that sits flush to the plastic outer enclosure cover by simply removing four flatheads. To avoid pulling or shorting of any of the wires when removing said side panel, a small terminal panel can be removed first and separately, so then the wires can dangle freely. And the next thing is the door. The door consists of three parts actually, the aluminum structural piece shown in the slide, as well as an acrylic window, and not shown is the ABS plastic covering. And collectively it weighs about 3 pounds, and so the torque of the door can be calculated to be 17.73 pound-inches. As a result, a suitable compact soft opening lid support is chosen. To open or close the range door, the user just needs to do a little tug and a little nudge, and the supports will ensure gentle movement and open or close the rest of the door. This is designed so that the door does not slam or cause any jams. So a set of two surface mount hinges attaches the door to the structural frame, and a simple static control handle is screwed onto the aluminum door frame. So here is a motion analysis video for spool replacement. This is a manual process in which the user removes a locking pin, swings out the spool base plate, unscrews the nut on top of the spool, and then the spool could be replaced with a fresh one. And next is a motion analysis video for the refill plunger when the vials are being discarded. So the linear actuator makes sure that the arm of the plunger applies a force to the stack of vials, and that force will cause these spring-loaded jaws to release the bottommost emptied vial. And here we have vial discarding times. So the separate motor that we chose has a max rotational speed of 600 RPM, and the ball screw that we chose can rotate 1 full inch per revolution. The gear tooth ratio is 18 to 30. So when we disregard motion, the motor acceleration and deceleration times, the minimum times for discarding the vials are shown below. So for a full sleeve of 6 vials in a stack, it takes about half a second to discard the vial. But if there's only 1 empty vial left in the stack, it will take up to 2 seconds. So here is another motion analysis on the manual placement of vials. So 6 vials of the same type and brand are being placed into one sleeve of the carousel. And here are some motion analysis findings. So the original enclosure box size and the hinge didn't allow the spool to fully swing out. Therefore, some changes had to be made to the enclosure box. We added 1.4 inches in width and replaced the lid supports with compact soft opening lid supports to allow enough clearance for the spool. And a different ball screw was used for the refill plunger because originally the ball screw can only turn 0.15 inches per revolution, and it had a smaller gear tooth ratio of 24/18, and a new ball screw is replaced. So the one we have now can rotate 1 full inch per revolution and a higher gear tooth ratio of 30 to 18.
The machine uses the speed and precision of computers and motors to automate the syringe drawing process, reducing the time required to accurately prepare a syringe by approximately 50%. By accessing and writing to electronic health records, it can also assist in maintaining patient logs, giving it quite the edge over antiquated manual methods of drawing insulin into a syringe. Most importantly, it reduces the likelihood of human errors, which unfortunately cause 57% of all US hospital dosage fatalities. It was our goal as a group to design a solution which could reduce this figure as much as possible. We hope that our machine design and analysis can be of some help to the medical industry. If produced after further development and refinement, our machine could help to save time, money, and most importantly, lives. This concludes our team's senior capstone design project, which was a great learning experience. Thank you, and go Bruins.